So friends, welcome back to this lecture on the application of AC to a pure resistor. And after I revise what I did in the first lecture, we'll talk about phasors and phasor representations and how our life becomes easy, okay, with certain assumptions. So we found that when we apply an alternating source of EMF, which as a source reads as V is equal to Vm sine of omega t, which I can write as capital V root 2 sine of omega t, where capital V is equal to the V effective or the V RMS value, okay, and it turns out to be equal to Vm upon root 2. So Vm becomes equal to root 2 into whatever you want to write here, which is 0.707 Vm, okay. Often in many a book we write Vm as capital Vm, okay. Doesn't matter, all these quantities are in volts. But the measurable quantity is this one, okay. And thus, if we say that there is a source 20 volts like the domestic source that we have, and we are drawing 1 ampere of current, it means these are the effective values, okay. They are not the peak values or the maximum value, which is represented by Vm. Well, as a result thereof, because as I told you, the resistor is a Raja beta, okay, is the prince of Tartary, so always spends whatever power is given to you is it goes out, okay. So joule heating is there. So I will be equal to Vm upon R sine of omega t. From this relation, you can see sine and sine, omega t and omega t. So there is no phase change. So that means the delta phase is equal to 0. So I can write this as Im Vm upon R as Im sine of omega t, which I write as I root 2 sine of omega t, like that, and I or I effective or I RMS, okay, is equal to Im upon root 2, which is 0.707 Im, and often like this I often write we write Im is equal to capital Im, okay. Another thing I told you was the power average over a cycle, a single cycle, that is a single time period, that is over a angle of 2 pi radians. This turned out to be equal to half Im square R, could also have been written as Vm square upon 2R, and Im by root 2 into Vm by root 2, which is I into capital V, okay. So, and in doing so, we had to, because when we square that term, then we get a sine square omega t or cos square of omega t, and we found and told you that sine square of theta is equal to 1 minus cos 2 theta divided by 2, and cos square theta is equal to 1 plus cos 2 theta divided by 2. And then I also explained to you that the average value of sine square theta is equal to half and cos square theta is equal to half, because the average value of sine square theta plus cos square theta is equal to always 1. When the two are equal, so they will share equally, like that. I also did plot the time diagram for V is equal to Vm sine of omega t, which is with the black ink over here, and I is equal to Im sine of omega t, which is with the red ink, where we have marked Vm minus Vm, Im and minus Im, etc. Okay. You can see that there is no phase difference, no lagging behind or ahead in time, whether we take it t or omega t, etc. I've just left that for you to complete. So delta phase in this case of the application of the alternating AC to a pure resistor and with the source having no impedance of its own, that is the impedance of the source, which is like the small r, and that is internal resistance, is taken as equal to 0. The sources we will take will be just ideal sources, and ideal source was taken over there also. Okay. Now this kind of a time diagram can be obtained, as I told you before earlier, in the case of simple harmonic motion by means of reference circle. I've just shown with the red one a reference circle representing the current, and with the blue one the reference circle which is representing the voltage. This one is expressed in the units of current, and this one is expressed in units of voltage. Okay, and when we rotate this, so there is a vertical component that will be equal to I sine of omega t, and a horizontal component which is I cos of omega t. Okay, like that we can obtain that. Now these quantities I and Vm, I and V, right? They appear to be, because I have put a sign like this and a sign like this, so it appears to us that they are vector quantities. They are not vectors. Okay, they are rather scalars. But we take advantage of our knowledge and our toolbox reference circle to learn the things related to capital I and capital V, etc., with the help of what we call phasors. Okay. So you see that I have just a phasor, Mr. A, maybe representing anything, we don't care, but they normally represent current and voltage, etc. Okay. You can see that here Mr. A does not have the two caps. The A hasn't this kind of a cap, arrowhead, or this kind of a cap, which is a sign of being vector. Okay. Instead, what they have, we have A, and here I have a plane, whatever you want to call to, there is no tilde, nothing, just a straight bar, A bar. Okay. So this is a phasor. Now we take advantage of the two-dimensional XY axis. Okay. So this axis makes an angle of 90 degrees. This axis, okay, x minus x, y minus y. Okay. Now suppose, now here is the beauty. If I rotate this phasor through pi by 2 or 90 degrees, I get a new phasor. And this rotation business, This rotation by 90 degrees we represent by small j, just a multiplier to a bar. Okay. So I get a new phasor which we will write as JA, like this. And if I rotate it further by another pi by 2, okay, then I get this operator. So what is my J? J is an operator which rotates the phasor by 90 degrees. And what I will get is J, A. Okay. So this double multiplier J, A becomes equal to J square A. Phasor. Okay. I'll not call it bar or anything. Phasor A. Okay. So naturally you can find that the angle between this phasor here and the other phasor in the minus x direction, minus x direction, and the total angle that is there is 180 degrees or pi radians. Okay. So there is a complete, we'll say that they are out of phase with each other, or they are in complete opposition with each other. So I can write this, whatever I have obtained here, J square A, phasor A, as equal to minus times, because this minus sign indicates the opposition. The minus sign says that it is in the opposite direction, and this we have been doing since long. So what do I get? This is minus this. J square phasor A is equal to minus phasor A. So from here we find that this J square is equal to minus 1. Interesting. And J square is equal to minus 1. This 1 is our 1, 2, 3, 4. That one. So J becomes equal to under root of minus 1, which is an imaginary quantity. So that is why on this xy axis, x-axis I write as the real axis, and this axis we take as the imaginary axis. Okay. So this kind of thing, now this is just like in complex algebra. Those of you who have learned about that complex algebra, there is an iota, not I, iota, which is equal to under root minus 1. So they have got similarity. So phasors will add, subtract, only two things I am telling you right now, like vectors. But what? We write that vector A plus vector B. Okay. When I say in the vector analysis that there is a vector A and there is a vector B, and we want to write an expression like this or like this, and then parallelogram law of vector addition, or the head to tail kind of vector addition, etc., etc., and we do those things. But I told you about an unexpressed, unwritten law about the vector addition. What is that? Which is normally not written in the books, but it is practiced definitely without mentioning that addition and subtraction, they desire that the vectors should be of the same family. Okay? They should be of the same family. Velocity, acceleration, force, this, that, same variant. Okay. It's not possible to add a velocity to an acceleration, for example. even a velocity to a what you call velocity and p, okay, this momentum, we cannot, okay. So this law is also adopted by us along with the vector addition laws for the phasors. For the phasors, they are not vectors. Phasors do add, subtract like the vectors, but the phasors are such quantities like current and voltage. We will first of all, when we draw something, it has a length, and that length should be proportional to the magnitude of the quantity that we are going to draw. So which kind of a quantity? I have my friend I and I have my friend V. Who are they? I and V. I is an RMS value. I is an effective value. V is an RMS value. V is an effective value. Okay. So my phasor, this I phasor, will have some length. Okay. And that length, when we draw that phasor, should be proportional to the magnitude of this phasor, or to the magnitude of this phasor. There is one point. The other point is that the phasor analysis desires that the voltage and the current be drawn on the same XY curve. What does that mean? Voltage has to be drawn in volts and the current has to be drawn in amperes, and they have to be drawn on the same thing. So that requires us to be vigilant. We should be always vigilant, and moreover, we should never be we should not fall in trap of adding a vector to phasor I to phasor V, subtracting phasor V from phasor I. So this is very important aspect. That's why I am saying time and again and time and again and time and again, and we'll keep on saying as long as we are using the phasors. So the units are different, the length associated, they are different, etc. Now, if we come across something like V and something like I, they are both scalars. If they were vectors, I could not divide vector V by vector I. I could not divide vector V by vector I. This is what we say, this is haram. This is not allowed. Okay, this is not possible. This is not feasible. This is nonsense. Anybody doing a vector division is an idiot, even if that idiot is yours faithfully. So, phasors. And phasors, once we have, we can talk about the resistor case as, for example, I'll just tell you about it. Doesn't matter. Now, what I have this real axis. V is equal to, I draw on this from here a phasor say V. Okay, this is the phasor V. And then I draw another phasor on the same line, and I can say that this is my phasor R. Okay. If they are rotated, we will get the time diagram kind of thing. You have to bear in mind how we are going to get that. But the one thing that is there, that the delta phase, this is very important, and that you will understand once we talk about the inductors and capacitors. So delta phase is equal to 0, and V and I are in the same direction, so that there is a real power loss equal to V and I. So then we will in one go, we'll talk about the inductors L and the capacitors, our friend capacitors, where I will write this plus and minus, and will just talk to you about it, that if I blow it up, it means that my capacitor has positive charges on the inside and the negative charges on the inside, but the print media does not allow us to put those signs inside, so you must understand it's like this. And the beauty is that when I have L, then there is Li square by 2, and when we have the capacitor, we have half CV square. Okay, I repeat, I got to repeat that if there is a phasor, and I call this phasor voltage for example, in one of the cases, and there is another phasor which is the I, and there is an angle here which I can say as angle phi. What it means? The axes are the same, but it shows that whatever be the contents of the circuit, R, C, R, L, R, L, C, whatever, then in this case what it shows is that the current phasor is always ahead of the voltage phasor. And if instead I have the voltage like this and the current is something like this, I am not purposely taking the phase difference as equal to pi by 2, then in this case you can see that there is a lagging behind of the current. Okay, here there is a leading current, and here there is a lagging current. I told you in the case of waves, as also in the case of simple harmonic motion, as to how you can see curves and tell which curve is leading which other curve. So the next two items that we are going to do, okay, because we have already spent quite some time, and we must spend that time for you to understand that here is a J operator, is a multiplicative operator, so the phasor, if 90 degrees still, then the new phasor, and of all of them, they will keep on moving in the anti-clockwise direction. So there is an omega and etc. etc. All these concepts has to be assimilated by us. Please read into the books, and I suggest that, because I have been quite fast sometimes, that please repeat this lecture at least 2 times. Okay, once, then again, and then you come at the same level, and when at the same level, we'll go in phase with each other. Else I may lead, you may lag, I may lag behind, you may lead. So that kind of thing about the phasors in general. Okay, and our Mr. J square is equal to -1 and J is equal to under root -1. This should be borne in mind. And of course, imagine, people have been imagining, but this kind of analysis, phasors and phasor representation, they were given by electrical engineers. Okay, so say hats off to them, because they have made our life easier. Because otherwise, there may be a second order differential equation to be solved and obtain the drawings, etc. accordingly. Okay. So for today, I leave you at that. And tomorrow very fast we are going to go through the inductor and the capacitor, purely inductive circuit, purely capacitive circuit, and thereafter we'll talk about RLC circuit, and from there we can make our conclusions for RLC series circuit. And I can just take off the L, then it becomes RC. I take out the C, then it becomes RL circuit. So, and we will introduce the reactance and impedance, inductive reactance and capacitive reactance, etc. And I showed you that these reactances are 180 degrees out of phase with each other. There is one more thing before I wind up, because you will say, oh, he didn't tell us this thing. That, you see, there is something called XL and there is something called XC, capacitive reactance, inductive reactance, and there is of course our Raja Beta R. Okay, they all have their units as ohms. They all are given by V upon I, like that, and to top these we have one Mr. Z. Okay, often what we do, we take a page out of the phasor representation to represent these things also. But whenever we represent these things, they are not rotating phasors. Here, anywhere, we are using rotating phasors. Okay, and remember that, please remember one more thing, or go back to that dd theta of sin theta or cos theta is equal to, sin theta is equal to how much? It is equal to sin of theta plus pi by 2, cos of theta plus pi by 2, and integral sin theta d theta, how much is that? That is equal to sin of theta minus pi by 2. Okay, cosine of theta minus pi by 2. So that part of my previous lectures should be consulted. Okay, and well, today, bye.